Hello everybody, and welcome to my quick Chapter 5 review over stereochemistry. It's kind of a confusing chapter, I will admit, so myself, but I think with a little practice and some intuition we can get there. So, what exactly is stereochemistry? Well, stereochemistry is basically utilizing Newman projections, structures, bonds, rotations, all of the tools we've been provided in order to determine whether the molecule is identical or not, and what kind of stereoisomer it is. So this is going to be utilizing a lot of nomenclature, Newman projections, and also you're going to have to understand just overall chemical formulas. So if you have these three skills, you'll be A-okay for stereochemistry. So let's begin. So first thing, we should probably talk a little bit about the different types of stereoisomers and the different type of just isomers. So to start it off, there's this thing called a constitutional isomer. I'm not going to write the isomer part because I'm a bit lazy. But a constitutional isomer is basically a compound that has the exact same chemical formula as another compound, but is just in a different connections, has different connections. But if I write out the chemical formula for this, they're going to have the exact same number of molecules, exact same number of oxygen, exact same number of hydrogen, exact same number of carbon, and that's all a constitutional isomer is. So these two are constitutional isomers. Another great example of this would be, let's say we have this molecule right here, and then I wanted to let me do this, and then we do that. So the nomenclature of this would be, well, actually, one second. Let's ignore that part. That's not you. That's a bit too complex of an example. Here's another simple example of a constitutional isomer. So these are also constitutional isomer, because if we use our skill known as nomenclature, we can tell that this is, so let's name these compounds, okay? Let's name both of them, and then I'll show you why this is constitutional isomerism. So this is pentane, and this is 1, 2, so this is 2-ethyl pentane, and this is 3-ethyl pentane. Now, if you don't understand how I name these, I highly suggest you go back and you learn nomenclature, because that's going to be a critical component for this chapter. Because we can tell if another good rule to know about nomenclature that we can utilize is we can tell this is a constitutional isomer because they have the same exact. They both have ethyl substituents, but they're connected at different points on this pentane. So we know that these are constitutional isomers. We can tell if a molecule is identical to another molecule by thinking this way. I'll give you an example. This might be a good exam question because he might give you something like this. not like that, my bad. Now, are these molecules identical, or are these constitutional isomers? Well, if I name this, I know this is 3-ethyl pentane, and I know that this is 3-ethyl pentane. So, if a molecule and another molecule have the exact same name, they are identical. So these two compounds, even though they're rotated, are identical to one another. And that's an important thing to know. Because we can determine this because we have such a strict naming mechanism. We have such strict rules when it comes to naming that if it's named the same, they are the same. So moving on to the next type of isomer. Let me go here, erase all this for you guys real quick. So the next type of isomer we might be dealing with is something called a conformational isomer. Now, we're not going to get too much into that in this chapter, but do know that a boat structure and a chair are actually considered conformational isomers. And all conformational isomers are basically the molecule bent or contorted in a way that changes its composition. So going from a boat to a chair is technically a conformational isomer. Kind of confusing to understand that, but that's one of the really only conformational isomers you're probably going to run into this chapter. So we'll breeze on over that. So now then, let's look at stereoisomers. Now there are two types of stereoisomers out there. You have, I might spell this wrong, an enantiomer and a diatomer. I definitely spelled that wrong, but you guys understand the point. So the difference between these two molecules is that basically a diatomer is an enantiomer is, I'm going to explain this with an example because it's much easier. So here we go. This is an example of an enantiomer. You see, only one of these flipped. The dash went to a wedge. And basically, that's all an enantiomer is all wedges or dashes have to flip at the exact same moment to be an enantiomer. If you have one flipping, like this, I have to be careful here, else I might draw a meso compound, so. If I go from this to this is considered a diatramer. I still can't spell that properly, but so this right here is a diatramer, and this up here would be your enantiomer. Now you're probably wondering to yourself, Ross, this is still kind of complex. How do I know where to start? How do I know where to draw the dashes? How do I know? How do I know? How do I know? Well, that's where I come in to help. Let's work through some practice problems real quick, dealing with this stuff. So, let me grab a practice problem real quick. hold on. You can fast forward maybe 10 seconds while I find this problem that I had. Okay. So say I give you a compound that looks like this. Actually, wait. Say I give you something that looks like this, okay? Now then, you're probably going to ask yourself, well, how do I know what has a dash and what has a wedge? Well, that's where we have to locate what's called the stereocenters, my friends. Now, a stereocenter is basically, think of it this way. It has to be a carbon atom. In our case, it has to be a carbon atom. There are exceptions in chemistry, but for our case, our class, what we're being tested on, it has to be a carbon atom. So let's look for carbon atoms on here real quick and highlight them. I got a carbon atom here, 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 and I got a carbon atom here. Now, there's another role that we can play into here. Stereocenters have to be sp3, meaning they have to have these carbons have to have 4 bonds to them. We can't have a carbon that only has 2 bonds. Doesn't work. So if we have something that looks like this, carbon, double bonded, boom, like that, say a hydrogen, say a chlorine, and say an OH group, well, I'm just going to tell you right now, that's not going to work. We want our carbon to look like this. Me is just a abbreviation for a methyl group, and a methyl group is going to look like that on your bond line structure. This is what we're looking for when we're looking for a stereocenter. Now, this might be a little complex to translate this into something like this to figure out where your stereocenters are, but it's still going to have these exact same roles. You still can't have an sp3 hybridized carbon. You also want to ignore all carbons that have more than one of the same substituents. In that case, what I'm talking about is if we have a carbon down here, and I have a hydrogen, an oxygen, and a chlorine, this isn't going to count. And you know why? Because I have 2 of the same substituents right here. So let's mark this one as not being a proper stereocenter. Moving on. The final role to ignore is any carbon basically that is connected like this. So if you have a compound that looks like this, and you have a center down right in here, well, we can already know that this is not going to be a stereocenter. You know why? Because from chapter 1 we know that boom, 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 there's 2 hydrogens right here. Once again, more than one of the same substituent, making it not a stereocenter. So if you can follow these roles and keep that in your head of why these stereocenters are stereocenters, you'll be okay in determining the stereochemistry of the compound. So once again, let's go back up to our little molecule up here, our friend, and let's take a look at him. So out of these, where do you think the stereocenters are? I marked all the carbons for you with a highlighter. Well, we know that this can't be one again, because look, 2 of the same substituents. So let me make this easy real quick, and let me do this. So we know that this can't be one. Once again, this definitely can't be one here. this easier to see in black so it looks the same color. We know this can't be 1 because we have 3 hydrogens here. That's not going to work. That's not what we want. And we can, once again, we know that over here, once again, there's going to be 3 hydrogens. So let's take a look at this guy right up here, this chlorine right here. Let's see. So we know there's a hydrogen right here. 2, 4, 6, 8. Oh, look at that. We hit the octet. We have a chlorine. So we have a carbon bonded to a chlorine, bonded to a hydrogen, bonded to a methyl group. Now I know this is a methyl group right here because this is just a carbon bonded to 3 hydrogen. So we know that that's a methyl group. Now let's see what's bonded over here in this direction. Oh, would you look at that? It's bonded to a carbon that's connected to an OH group. My friends, we have found our first stereocenter. So now we have 1 stereocenter. We can mark it. Mark it however you want to mark it, but I highly suggest you mark it. Let me go back. Get this, like this. 1 second. Mark this. 1 second, guys, while I clean this up for us. Actually, I'm going to redraw it just to make this easier for us. So, boom, 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 boom. So we now know that this right here is a stereocenter. So we have 1 stereocenter down. Let's see if there's another one. Well, we can do the same thing with this OH, or this carbon right here. We know it's connected to an OH group right here. We know it's connected to a methyl group right here. And we know it's connected to C2 right here. So this is definitely another stereocenter. So now we have our stereocenters. Let's move on. We also, well, we'll go into that in a little bit about meso compounds. This is not a meso compound. So let's erase this and redraw it up here. When drawing out your stereoisomers, we can use a neat little formula. So N, use 2N to determine how many stereoisomers you need if there's no meso compounds. Only works if there's no meso compounds. Okay? So we don't have a meso compound. I can just tell you. I will go over in a little bit, but I can just tell you. There's no meso compound there. So we can use this formula right here. 2N. So this would then be 2 to the second. Now, for you math whizzes out there, 2 times 2, quite a complicated formula. Oh no, what's it equal? 4. So this compound has 4 total stereoisomers. Okay, so I'm gonna erase this. Okay, I'm gonna move this up here. So how are we gonna find these 4 stereoisomers, my friends? Well, let's just start drawing. Okay. So I like to start them all out on wedges, okay? So we have this. This is a stereoisomer. Here's 1. Now let's just start changing stuff on here. Change 1 at a time. I'll change this chlorine. Keep this the same. Now then, I'll change this OH. and I'll keep that the same. And now then, to get a completely different looking thing, I will change this chlorine. Would you look at that? 4 total. And these are your stereoisomers. Now we can go one more into it, and we can label what's an enantiomer and what's a diatrimer. So from here, so if we're going from here to here, these would be enantiomers. Okay? Now these are enantiomers because both wedges are turning into dashes. So that's why those are enantiomers. Now then, if we're going from here, I'll color code this for you. So black is enantiomers, green, the green arrows are going to be your ditramers. Now then these two are ditramers right here. The first and second are ditramers because we only have one wedge turning into a dash. Okay? Now then, same for these ones. So the green are once again going to be the exact same. One wedge turning into a dash. So I'll label these for you guys real quick so you can even follow along a little better. And if you have to go back and watch, I highly recommend. So 1, 2, 3, 4. Now then our final compound, which is right here, number 4. And number 2 are once again enantiomers because we have both of them changing at the same time. So the wedge turns into a dash and the dash turns into a wedge from 4 to 2. So now then that we have all these labeled, let me just write these out for you. Let me move this up here. So we have 1 to 2 is going to be an enantiomer. I mean a ditramer, my bad. Ignore that last part, guys. I'm still probably spelling this wrong, but you understand where I'm coming from. 1 to 4, also a ditramer. 1 to 3, an enantiomer. And now then, let me see, what one am I missing? Oh yeah. 2 to 4 equals an enantiomer. And then, let me move this up. Then we have 2 to 3, which is also would be considered a ditramer. So now that you understand this, let's move on to something else. Actually, I want to go back over stereocenters because I feel like that's very beneficial and in a more complex setting. So let's go with a more complex stereocenter. So let's go with a compound that looks like this. Let me see. Okay. 1 second, guys, while I draw this out. Okay. So, on this compound, let's find the stereocenters. So once again, definitely not. I'm going to mark the ones that are not stereocenters in red, okay? Not a stereocenter because it's SP. It's not SP3 at all. Not a stereocenter. Not a stereocenter. Not a stereocenter. This is a potential stereocenter. This is potential stereocenter. This is not a potential stereocenter. This is not a potential stereocenter. This is not, this is not, this is not, this is not, this is not. This is. So let's draw these out. I got carbon bonded to an oxygen. For this one right here, we're going to draw it out real quick. Down here. So I have a carbon bonded to an oxygen, which is bonded to a, let me see, 1, 2, 3, 4, 5, 6, cyclohexyl. So, a poorly drawn cyclohexyl, but you guys get the point. And then it is also, wait. My bad, guys. Did not mean to draw that bonded to the oxygen. It's supposed to be bonded to the carbon. Okay. We also have this carbon bonded to a hydrogen, and we have it bonded to an oxygen group like that. A carbon bonded to an oxygen. So we can attest, my friends, we have found a stereocenter right here. So mark that, asterisk it, however you want to do it. Just mark her down as a stereocenter. Okay, let's look at this one right here. Let's go in here and let's check and see if it's a stereocenter. So, looking at this one, we have this group over here, which I don't even want to name right now. And I'm not going to name it because we don't have to name it. We just have to know that that's a different group. We know that this over here is a different group because of the oxygen right here. And we also know that there's our hidden hydrogen right here. Once again, I highly recommend, you're going to have to use all your skills for this chapter. So make sure you're keeping up on it, or else this stuff is going to seem like rocket science. It is a very difficult science, but it's not rocket science. So now then, we do know that we have, count them out with me, 1 group that's different, 2 group that's different, 3 group that's different, and we also have another group that's different because this is a methyl down here. So we found another one, guys. Let's mark it right here. So on this, we have found 2 total stereocenters, and we know it's not a meso compound. So let's do 2 to the second power. What's that going to give us? 2 times 2 equals 4 total stereoisomers. So we have 4 total stereoisomers for this compound right here. Okay. Let's now go over, I think it's time we deal with the meso compounds. The meso compounds are kind of complicated. For example, if I give you a compound that looks like this, and I give you something that looks like this, can this be a meso compound? Oh, I should probably label this for you. Say this is bromine and this is also bromine. Well, I hope you took a minute to think about it. These 100% are meso compounds, because if I draw a plane of symmetry down this, they're identical to one another, 100% identical. And if I draw, I'm not going to draw that for you, but you know this can be a meso compound because there's a line of symmetry going down this compound. Okay? So, what's a meso compound mean? Well, we know that this is going to be a stereocenter, and we know that this is going to be a stereocenter. And let's also, we'll practice that at the end. We know there's 2 stereocenters, so hypothetically it shouldn't it be 2 to the second, meaning there's 4 stereoisomers? Well, that's actually not true, because a meso compound is the exact same compound as the exact same stereoisomer as another stereoisomer when you draw them all out. So let's draw these all out, all the stereoisomers out for this meso compound. So we have our cyclohexane, we have our 2 bromines, bromine. Now then, like the rule I taught you last time of how I like to draw these out, change one at a time. Don't get fancy with me and start changing 2 at a time. Change 1 at a time. Slow and steady wins the race, boys. I know these are poorly drawn cyclohexanes, but hey, I'm not an art major. Never said I was. So, as I'm drawing these out, can you guys notice anything weird? Oh my gosh, that's a very bad drawn cyclohexane. But we're going to throw it over. That's a cyclohexane, I promise you. This is a cyclohexane. Oh no. This is a cyclohexane. I promise. I promise you it's a cyclohexane. So, now that we have all of our uniquely drawn stereoisomers, is there anything you guys can tell me about these compounds? Well, if you realized that this bad boy right here and this bad boy right here are the exact same compound, then you're 100% correct. Now then, we know these are the exact same compound, because if I draw this out, and it's chair conformation, and I have both of these down, so this would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. These are both in equatorial. This is going to utilize your chair flipping skills, guys. And this is also in equatorial. Now if I flip this so that it's going from, my bad, that's not how we're going to do it. Let me move this up to here. And actually let's move this up to here. And let's move this up to here. And so we flip this. And if you remember from my last lecture that I had, reverse llama versus forward llama, this is my reverse llama, and I'm going into forward llama. So now that when I flip it over, this is going to go down 1. This is going to be going down 1. These are now both axial. So that's the same exact thing. Same distance away from one another, same everything. These are identical to one another. Now, you don't have to be a champ at doing chair flips to understand that these are identical. Just know that they're For now, the role is going to change for meso compounds if I give you something different, which we will look at next. But a good rule to know is that if you have two wedges and they have a plane of symmetry, which we do, and they go to two dashes, and it's a cyclohexane or pentane or something like that, and they're equal distance away from each other with this plane of symmetry, and they both go to dashes, don't think that that's an enantiomer, because that's not actually an enantiomer. That's just wrong. This is a meso compound. So you're probably asking me, so Ross, now that we identified that, yeah, those are both the same, why aren't the others the same? Well, the others aren't the same because let's draw that out real quick. If I have, actually, let me go take that back, and let me actually take this. Let me do this real quick. Sorry guys, just gotta clean this space up for you guys a little bit so you guys can better see, better understand. You're probably wondering, Ross, why aren't these the same compounds? Why is this and this? Why aren't these meso compounds? Well, let's draw it out. Forward llama, and we have 1, 2, 3, 4, 5. On the first one, I have my bromine going up. 1, 2, 3, 4, 5. On the fifth one, 1, 2, 3, 4. 1, 2, 3, 4, 5. I have my bromine going down. So now then if I flip this, there you go, so boom, 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 boom. So if I flip this, this would go here, so we'd have this here, it'd be up, and then this would go here, it would still be down. Well, what do you notice? Why aren't these the same anymore? Well, I can't, no matter how I change these, I can't get them to fit on each other. The other one, you really need a molecular kit to understand this. The other one you could easily fit on one another. But for this one you can't. No matter how hard I try, I can't get these to perfectly line up. Just like I can't get my hands to perfectly line up. On the other one, I sure can get them to perfectly line up. And I highly suggest you build this in a molecular kit to prove this. But if I try and put these together and superimpose these, I can't do it. It just doesn't work. So, these would be enantiomers to one another. These are enantiomers. And for our two meso compounds right here, for this meso compound and this meso compound, well, we got to figure out how we put these into total unique stereoisomers. We can't just say we have 4 unique stereoisomers because one of these is not unique. So now then, I'm going to give you a little formula. When you're dealing with only 2 stereocenters, you can do 2 squared equals 4. So we have 4 stereoisomers. However, we have to account for that one meso. So it's going to turn into 4 minus 1, giving us, pick one. Or, I mean, there's another way. You can just label these as meso and you will be correct. But there's only 3 unique stereoisomers for this. Okay. Let's do another problem, a bit more complex of a problem. Give me 1 second while I grab it real quick. Enjoy the soft music while I go and grab one thing real quick. Okay, I am now back. So for this meso compound, we're still going to be working with a meso compound, but I want you to tell me why this is a meso compound. So I hope you guys by now are okay at drawing out compounds, because on the exam, you're probably going to have to draw stuff out. I'm not going to lie to you. So let's draw this out real quick. We have hexane. So let's do 1, 2, 3, 4, 5. Oh no, did not mean to do that. Let's now label these. So we got 1, 2, 3, 4, 5. Now then, let's connect the dots. Just like you're a child again at birth. Connect the dots. 1, 2, 3, 4, 5. It's hexane actually. I completely messed that up. So I did not account for that. Put the 6 here because hexane is 6. So now then we have tetramethyl. What does tetra mean? Will the world ever know? Well, tetra just means 4. And I believe it's in some ancient language like either Greek or Latin. But that is not relevant for organic chemistry. So we know that we're going to have 4-methyl. Now where are these methyl located at? Oh no, where, Ross? Where are the methyl located at? Well, we're given the coordinates right here. So, let's put it down. We have 1 at 2, 1 at 4, and 1 at 5. Because it's 2, 4, 5. And we also have 1 at 3. My bad. I labeled this wrong. I gave you guys a stinker. I didn't even realize I wrote that wrong. But it's 2, 3, 4, 5. So we also have 1 at 3. And if you remember, this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Now, what's so interesting about this? Why do we know that this is a meso compound? Well, you're probably like, Ross, there's no symmetry in here. I don't see any symmetry. Well, I'll be here to tell you there's definitely symmetry. Look at that. A line of symmetry within the molecule. Okay, so now that we know this is a meso compound, let's draw them all out. How many stereocenters do we have in this though? We have to remember, account for stereocenters now. We know it's a meso compound. We know it has that line of symmetry, but first, let's determine what's going to have the wedges and dashes and how we're going to draw this compound. So, I'm going to label all the carbons on here like I always tell you to do. And look at all the carbons and see if they're meso compounds. I'm going to put red X's through the ones we can automatically get rid of as not being stereocenters for the roles I taught you earlier. Okay, so let's look here. Can this be a meso compound? No, because there's a methyl here. That's not a meso compound. Can this be a meso compound? Well, maybe. We'll come back and look at it. We know that this is identical to over here, so can this be a meso compound? Right here. This cannot be a meso compound. So, we now have... Wait 1 second, I forgot. I was not even paying attention. Can this be a meso compound? Let me check real quick. Can this be one? Can this be one, Ross? Well, the world may never know. Well, I'm here to tell you that this is a meso compound, and this is a meso compound. Why is that? Well, if we look at this, we have, for this one right here, we have a carbon bonded to an isopropyl group, bonded to a methyl, bonded to a hydrogen, bonded to something that looks like this. So yes, this can be a stereocenter. So there's one stereocenter. One stereocenter right here. So let me erase that. Can this be a stereocenter? Well, let's take a look. Can this one right here be a stereocenter? Well, we got a carbon, we got a methyl, we got an isopropyl, we have a hydrogen, and we have this weird looking thing over here, which if we really wanted to name it, we can. Would you like to really name it right now though? No, because we're not doing full-on nomenclature, and that wouldn't even be accurate for nomenclature. But we can tell that yes, this right here that I'm circling is a stereocenter. So we know we have two stereocenters, and we can do 1 plus 1 gives us 2. 2 squared equals 4. Now we know this is a meso compound. So minus 1. We're going to have 3 unique stereocenters. So 3 unique stereocenters. Sounds good to me. Let's draw them out though now, guys. So if we have 3 unique stereocenters for, let me see, 1, 2, 3, 4, 5, 6, and then 2, 3, 4, 5. We know that these were our stereocenters, so let's start them off on the wedges. Let's change one thing at a time. So well, that's 1 second. I drew that not how I want to draw it. And now then, let's now then change this. Keep this the same. So there are our 4 stereoisomers. Now then, which ones are the exact same? Well, we have to look at this and think we can't use that same rule that we used on the cyclohexane or the pentane or anything like that. We have to think of it this way. We're looking right here at these 2. And you're probably going to want to say, hey Ross, these look quite the same to me. Well, I'm going to tell you that they're definitely not the same. Because if I go down and I look at this, if I'm looking from this carbon right here to this carbon right here, so think of it this way. You have your carbon, and you have your methyl group behind here, and then you have a hydrogen popping out at you, and you have a hydrogen straight up. And then over here, you have your carbon, and you have your methyl group out at you, and you have your hydrogen popping out at you, and then you have it bonded like that. Well, actually, this isn't a hydrogen. This would be just bond right here. It wouldn't be a hydrogen. It'd just be bonded to another carbon. Well, let's draw, that's this. So let's now look at it from another angle. Let's move this arrow right here. So what's this one gonna look like? Well, you're gonna have a carbon, and then you're gonna have your methyl group popping out at you. And you're gonna have your carbon over here, and you're gonna have your methyl group popping out at you, bonded to a carbon, and then you're gonna have your hydrogen, and then of course that. So this is when we're comparing these two to see if they're identical. If I rotate these, am I ever going to be able to get them in the exact same spot as one another? Ever? Am I ever going to be able to get, no matter how much I want to try and rotate this molecule and this molecule, am I ever going to be able to do it? To get them to line up perfectly. I mean perfectly. You're like, oh yeah, you can, because in that, they're going to be identical. No, they're really not. Because they're not the same. No matter how I try and twist this, it's not going to be the same. So I can draw this another way to show you better also, which I'm going to do for you right now. So, let me get this out of the way. When I draw this, let me get these out of the way. We know there's 4. We went over the 4. But now we're trying to prove which one's the meso compound. So, boom, 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 boom. 1, 2, 3, 4, 5, 6. Methyl, methyl, methyl. And we know that these are our stereocenters. So when we're trying to compare and see which one are our meso, no matter how I twist this, because if I translate this, if I twist this bond right here, and I twist it into an object that kind of looks like this. Say I bring this one down so it's like this. And then this is twisted so that it's up. And then we have it like this. And then I bring this one up. Well, this is actually gonna turn, this methyl right here, when I twist it like that, is gonna then start sticking up. And the hydrogen's gonna be back. And this one, when it's twisted, it's actually like that. So when I twist it to make it look like this, I can never make it look like this one, because when I twist this one to look like that, oh wait, my bad. When I twist this one right here, and I bring this down, because when I'm actually trying to make these look identical to one another, I can't do it. Never will work. Because when I do this, this is now going to be like that. This is going to be like that. And no matter how hard I try now, they're just not the same. Now then these ones, right here, these are going to be your meso compounds actually. Let me draw these out for you. So I have boom, 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 boom. Did not mean to draw it like that. Why are these actually our meso compounds? Well, I'll show you why. Because when I twist this, it's still going to be popping out. Oh no, no way. Could it be? Could this be the reason why? Could this be the reason why these are actually identical compounds? These are the same. Because if I flip this over, of course the methyl would be popping out at me. So all I'd have to do to get this one to look like this one is flip it. Just flip her. That's all. They line up perfectly with one another. These are the meso compounds. And it's because of that folding and twisting of the molecule that we can tell that those were the identical ones. So if you actually had to draw it out, you could either choose to draw both of them, or you could identify that as a meso, and this would be your answer. 1, 2, 3, 4, 5. And you'd have 1 second. this would be your answer. You could choose either the miso compounds, or you could draw them both. I mean, it's up to you, but just make sure you label it as miso. Know that that is miso. And then so this would be your final answer. We have 3 unique stereoisomers for this. Okay, now I know this has been going on for a while, about probably a good hour, so let's finish it up. Okay, I want to talk about the RNS system real quick. I might make another video separately for the RNS system. We know enantiomers, ditramers, miso, but I just want to introduce you to the R and S system. So the RNS system, before I start my next video, we should know this. Write out your entire periodic table. Okay. So now that you have your entire periodic table labeled out, memorize these numbers. These are going to be called what are called, underneath each molecule or atom is going to be your atomic number. Okay? This is the easiest way to actually do the RNS system. So now then we have here these are the blue, I'm going to label right here, are your atomic numbers. Now when you're comparing for the RNS system, so when you're labeling, do this real quick, sorry, 1 is going to be least prioritized. And the higher the number, so anything in the larger, so say 100, most prioritized. But you have to understand this chart to be able to do that. And I highly suggest you memorize this chart, because we are going to move on to one problem, and then I'm going to upload another video probably tonight or tomorrow going over practice problems with the RNS. But I want to get this one out for you guys tonight so you have something to reference. So let's get rid of this. We're going to go over one problem real quick. Boom, boom, boom. I got a bromine. Now then, let me move this. So, is this R or S? Well, the world may never know. Actually, I'm joking. The world is going to know, because I'm going to teach you how to do it. And you guys are going to be chemical badasses after learning how to do this. So, we know this is a stereo center because I just taught you that. And I know you guys are smart and remember that. So, we know this is our stereo center. So, let's draw it out. I got bromine. I got a carbon. And our bromine's going to be on a wedge. Our hydrogen's going to be on a dash. I got my methyl group, and then I got my carbon group. Well, you're probably like, Ross, this is also carbon right here, and this is carbon, and this is carbon. Oh, God, too many carbons to deal with. Well, calm down, because this carbon is bonded directly to a hydrogen, and this carbon is bonded directly to another carbon. So we know from that chart that this, of course, well, we can always mark off as hydrogen as number 4 priority. Bromine, that's going to be number 1 because of atomic weight directly attached to bromine. Methyl, probably number 3 because this one's bonded to another carbon, not a hydrogen. So this would be 2. Now we remember, you always have to have your dotted bond to be your 4th priority. Always has to be that, or else it's not going to work. So now then, if we draw the Newman projection of this, we look at it like this up here. We have bromine. This is not how you actually draw Newman projections. This is just a way to tell if your priorities. You got a methyl 3, and then you got your carbon at 2, 3, 2, and 1. Now, what direction is this going in, my friends? Well, that's going clockwise. I hope you know what a clock is. What way a clock ticks is going to be R. So, R equals clockwise, and S equals counter. Because actually S is derived from the Latin word sinister, meaning opposite. So, we got counter, we got clockwise, and we got R. Because we are going clockwise with these priorities. Get rid of that hydrogen, it was 4th priority and it was on the bond, it was on the dotted line, so it was behind. We can ignore it. So this bromine is R. Now you're probably like, Ross, how the heck do I now, what is this going to do to, how is this helpful? How is this helpful? Well, there's a couple ways it's helpful. I'll go over the main ways in the next video. But for right now, it's helpful because it's going to be helpful for nomenclature. You're going to have to name this. So what is this? Well, first off, use your nomenclature skills overall. We know that this is 1, we know this is 2, we know this is 3, and we know this is 4. So this is going to be, put in the brackets, 2R, 2 bromo, 1, 2, 3, 4. Butane. Boom. You guys just understood what the R system is. And I'm gonna leave you guys on that. I will be dropping another video tonight, and I really enjoy making these videos. I love to help people. I love to help a fellow student. And I want you guys to all know you are amazing, and you guys are gonna kill this class. So I leave you guys with that. Have a wonderful night, evening, day, wherever you're watching this from, and I will see you next time.